So good evening, everyone. Hopefully you can hear me and also see the screen I'm sharing. Um, so what I will be starting on a new lecture slide set today, but a couple of announcements. So firstly, I will stick around after the lecture because I know many of you are still actively trying to decide your projects. So if you want to talk to me, I'll be around for half an hour or so after the lecture. So come and talk to me. I think many of you have now are well on your way, but identifying a project, but some of you still need some help. So please come and talk to me. Second thing is I wanted to sort of take care of some loose ends from the video on Android development that you saw last time around. Unfortunately, my postdoc didn't do a then explain kind of the actual software development part very well. So I just wanted to those of you who are uncomfortable with have never used Android tools and all before, so I just wanted to walk you through it very quickly so that you know what's going on. So basically, if you recall, there were two examples that sort of that lecture had mentioned. One was a sensor demo and another was a camera demo. So firstly, if you follow the link on Piazza, you will get to this particular GitHub site where you see the Android examples being present, okay? And what I've done is I have put some brief instructions there, what we need to do in order to be able to run them. Also, if you had followed them last Wednesday, then once I tried them out with the latest release of Android tools, I realized that they didn't work. So I fixed them. So at this point, if you were to follow the instruction, re-download and all, they should work fine on the latest Android tools and the latest current versions of Android OS. So what you would need to do is to download this. So I'm basically, there is a repo for the course where right now all it has is this particular thing. So you kind of go to the code and download the zip file, unzip the thing, and then go under software Android examples, and you would find the two examples. Okay. The second thing you need to do is to go to Android Studio website and you download the Android Studio. This one shows 4.1 for Mac because I'm on a Mac, but this is available for all the other, both Windows and Linux as well. Okay. Now, when you download Android, it basically downloads the IDE and all. Then when you start up, at least on Macs, it looks something like this. Any previous projects you have opened, in my case, these two, since I recently opened, so they show up out here. But the first thing that you have to do is to go under configure. And if you don't see it out here, then maybe it appears somewhere else on Windows and Linux. I can't say for sure. But you go under this, and then you have to go under SDK Manager and make sure that you have downloaded Android 11.0, which is a very first option, which is the latest tool. So that's under the SDK platform. You should basically make sure that typical things like Android build tools and all are all downloaded. So kind of just basically go through this to download things. So that's one stuff that you will have to download. And in my case, what I did was I downloaded a lot of the recent Android releases, but you don't need to do it. Just Android 11 is sufficient. The other thing is, if you have an Android phone, great. If you don't have an Android phone, then you can also download a virtual device, which basically, as I will show shortly, opens up kind of a screen on your laptop where you can at least look at how things look like. Unfortunately, since we are doing things with camera and sensors, so you can't really mimic them on the laptop, or at least I don't know whether it can. So I downloaded a Pixel 4 XL API 30, which is the same phone that I work with for Android development. So again, you kind of download this virtual device. And then finally, you're going to open the existing project. So in my case, it's already there. So let's go with this sensor demo. Okay. So, yeah. Oh, one other thing. If you have a real phone, then you have to set the real phone up for to be in the development mode. So let me show how that happens. So hopefully you are seeing my Android phone. Let's see. Okay, I need to. So to set an Android phone into development mode, you will have to go to settings. You go all the way down to about phone, and then you go all the way down to build number, which is okay. This is kind of rather annoying. Let's see. Okay, so you go to build number, and you will have to press it 7 times. Now I already did it, but this is how you make your phone enter into turn it into a developer's mode. That's the standard Android thingy. And then you will also have to go. I have the instructions there. I forgot, but you have to go and maybe in the system, advanced system, USB. There is a place where you have to set it into a USB development device. Anyway, you can follow the instructions, so which are on the website, or I have the link to there. So you have to set your phone into the developer's mode. Once you have done that, then you fire up this and you get into kind of the main project. Let's see. Okay, so this is a sensor demo thing. What you'll see is a whole bunch of stuff. It should basically run, but I just wanted to show you that the actual code is sitting under this app main Java. Okay. And there are 2 activities. There are 2 kind of screens which show up under here. You are going to build it, and then after that you are going to select the right device. In my case, it shows both the hardware phone, Google Pixel 4 XL, as well as Pixel 4 XL API 30, which is a virtual phone. So I'm going to just first let me show you how it might look on the virtual device. So if I selected this virtual device, then if I run it, yeah, it's not running while API is not. Okay, let's see. Hopefully it will work now. Okay, so if I run this thing, you see it fires up this emulator, and this emulator came up, and and this mobile let's see. Okay, so it takes a while. So now it fired the sensor demo. In the sensor demo, the very first screen is where you just okay, and then it goes into this other screen, and kind of the idea is if you were on a real phone, once you press a button, then it will reflect the actual accelerometer values that show up. And if you make the accelerometer very large, sorry, acceleration very large, then it makes kind of a sound. And you can see all of it being reflected. So there is this main activity, which is where, if you would see, it asks for it asks for the name. So kind of there is a text box and all that you see, text message that we had seen. There is a button for continue. There is a screen. So all of this sets up that initial screen where I had typed the name, and the second activity is where you see those 3 fields: text X, text Y, text Z, which is where the accelerometer values are. And then you see in this area, it actually gets the sensor service, type accelerometer, this is where it is actually getting the three fields where the text values are to be stored. And then every time a new sensor reading is obtained, it converts it into, it gets the value from the sensor event. So basically what Android operating system does is every time it takes a new value from the accelerometer, it pushes it to the app. You get an event, and there are three fields in the sensor event of type accelerometer, and then it converts it into string, and then it puts it up there. Another thing which it does is it checks what the energy in that value is. So essentially, it's doing the square root of the summation of the sum of the squares, and it calculates the norm of the acceleration. And if it is greater than 15, then you see that it plays this sound, and this sound is r raw.crash, which is sitting under, in Android, these things go under resources. So it would be sitting somewhere here, resources, raw, and this is a sound file, crash.wave. So essentially what this app does is um, it shows the acceleration values, and if the acceleration is large enough, then it will make a sound. And the first screen, you have the name. So now let's try it out and see how you run it on the real device. So just give me a sec to unlock my phone. Okay. So now I'm going to, this time around, I'm going to run it on the real device. So I'm going to select the real device, and I'm going to hit run, and back to my camera. So now you see the phone being shown. Okay, and hopefully you can see it. And now you see the same screen that I said. There is a button, and there are three values. Okay, for some reason it's too whited out. So if I hit the button, it starts showing the values, which are a little bit hard to see, unfortunately. But if I uh, I shook it, and then you can, that crash sound came in. Okay. So anyway, so this is the app running on this. Um, the second app is the app which. So I'm going to terminate this. Waiting for process to detach. Disconnect. Okay. Okay. The second app is this camera app, and what it does is, again, in this app there is a single screen main activity, and all it does is it basically lets you take the image of a camera. It kind of shows that how to do an image capture. So some of you might be doing projects where it requires you to access the camera, so you can look at it and see how things work. Again, the process is the same. You kind of run it. So let me show you how it would look on the emulator. Um, so and these things at the bottom show you the different terminals and stuff like that. So kind of a usual programming environment that you might encounter, except, like I said, it has these uh, things which let you emulate and also. Anyway, this is a build. Now I'm going to run it. So let's go to, let's see what happened here. Just give me a second. Okay. So now it fired the app. The emulator obviously is a little bit slower. So this is what the screen looks like. And kind of the idea is if I do a take photo, then it will, okay. So in this particular case, if when I press this thing, it says need camera permission. So you'll have to go into your settings and make sure that this particular app, which is called mobile object, has the permission to take the photo. And then after that, the photo you take will appear where this little Android is. Anyways, so these are meant to be just very, very simple examples. There is lots and lots of code. And also if your project involves making an Android app and all, you might want to just hunt around and all and look for sample code and all from GitHub. But kind of the basic idea is what you are seeing. And besides Java, this thing also supports a language called Kotlin, Kotlin, which has some more interesting features, but I doubt any of you are familiar with it. And also some simpler apps you can even write in other languages, even simpler languages also. So but this is the right way of doing kind of Android app development. So that's all I wanted to show, because after last lecture, there were a couple of you who had asked me on like, can I give instructions on how to run these things on the actual devices. So obviously, if you are doing a project around these things, you will have a real device, and so you should be working with that. But and those of you who need to work with iOS devices, you're welcome to contact me, and I can point you to some resources there as well. Okay, so that is all I had. Any questions on this whole from last Wednesday's lecture or video rather that need clarification? Okay, so if nothing, then I want to start on where we were at the very end. So let's. Okay. So towards the very end, I kind of rushed through this thing, but we were basically talking about how do you do and how do you make sure that there is no deadline misses. And if you recall, we had gone through kind of a couple of formulas which were kind of a sufficient condition. But then if all else failed, then you have to kind of do this exact analysis. And one way to frame this exact analysis is to compute that for every task, the response time, Ri, fits within the deadline. And in order to be able to do it, we had constructed this equation, which showed that the response time of the ith task is equal to the time it takes to run that task, plus the interference which comes from all the tasks which are higher priority than this ith task. So HP of I is the high priority. And basically what was happening was that any task which is of higher priority, that will come Ri over Tj ceiling times, because if it is higher priority, so worst case, it also comes at t equal to 0, and then a few additional ones which will come in. And then each one of those instances for the jth task will take time Cj. So this is the interference term. And we basically have a fixed point equation that is an equation on the form x equal to fx, and we have to find the solution to x. This is a nicely behaved equation, because if we iterate, as we show out here, that is, we start with an initial value of r sub I and then keep iterating. So we get a new value, plug that back in and keep iterating, and this value will always increase because the right hand side is strictly increasing. And the net result is that we can create this simple algorithm where basically we have a loop, this loop and loop, where we are doing that iteration, and then one of the two things will happen. Either at some point, the currently estimated value of Ri, which is this, will exceed the deadline, which is T sub I. And if so, we basically say that, look, this task is not meeting is not meeting the deadline, and therefore we fail to schedule. Or alternatively, what may happen is that we may find the solution, which is the new value of R sub I is equal to the value from the previous iteration. And if so, we have found the answer, R sub I, and then we exit with the value found. And we have to do it for every task. It's not sufficient to do this thing just for the lowest priority task. That's a very important point, because it's easy, you can easily end up cases where if you that your lowest priority task may work, but some intermediate priority task may fail its deadline. So it's very important that you do this test for every task. And the other thing to remember is this stuff is only valid when deadline is equal to period. If deadline is less than period or more than period, then you need kind of then our results change. So what changes about it? So what is true is that if deadline equal to period, then rate monotonic, namely we assign priorities according to the rate, that result only applies when deadline equal to period. But this way of checking for the deadline misses also works if deadline is less than T sub I. And all you need to do is you replace this, that the current iteration value is greater than T sub I, you will replace it with the current iteration value is greater than deadline. So if deadline is less than period, this with a slight modification, the same algorithm still works. If deadline is greater than period, then things get harder. And the part which gets harder is that now it is possible that there are two or more copies of a task active at the same time. And therefore, one needs to sort of modify this basic algorithm even more. So thus far, to summarize, what we have is if deadline equal to period, then first thing we know is that assigning priorities according to the rate. So higher the rate, higher the priority is optimum. Optimum in the sense that if that priority doesn't work, then any alternative will not work. So that's result number one. Result number two is that if the utilization meets those two theorems, two results we had. So I'm just kind of going back. We had this result. Let's see, where is it? Yeah, that if u is less than equal to this value, n times 2 to the power 1n minus 1, so u is the total utilization, then we know that we can schedule it, and we can certainly and the rate monotonic assignment will work. We had a better result. So this also, so if your task set satisfies this result, then again we know for sure that it can be scheduled. And since we know it can be scheduled, so rate monotonic will certainly work. Again, remember, this result is for deadline equal to period. If deadline is not equal to period, then these results, this result and this one, they do not apply. Second thing is that even if deadline equal to period, and let's say this equation is violated, this inequality is violated, then you would have to conduct the full-blown test, namely this algorithm, in order to verify, because it's possible that that equation was violated, but still it was schedulable. Now, this obviously is a costlier procedure, so you should first check that quick way. Now, that's the baseline theoretical framework, and then there are all sort of relaxations on top of it. So what happens if the deadline is not equal to period? So one case that often occurs is deadline is tighter than the period, and of course deadline will have to be greater than compute time, because if deadline is less than compute time, then obviously I can never meet it. Now, it turns out that for this particular case where deadline is less than period, the rate monotonic assignment becomes deadline monotonic assignment. So instead of saying that the highest rate task is the highest priority, or in other words, longest period task will have the lowest priority. Instead of that, we will basically say that the task which has the longest deadline, as in from arrival to deadline, arrival to completion, that time period is the longest, we will give that the lowest priority. So basically, it's called deadline monotonic priority assignment, but very simply stated, it basically says that we are going to assign deadlines in inverse order to the relative deadline. So for example, what you see out here, what happened to my cursor? This is it. Okay. So if you see this task set, it has period 20, 15, 10, and 20. So if I were to be doing rate monotonic, then task 3 will have the highest priority. But our deadlines are not equal to period in this case. So deadlines are 5, 7, 10, and 20. So what this is saying is task 1 comes every 20 time units. And whenever it comes, we have 5 time units to finish it, and its computation time is 3. So what in this particular case, deadlines are less than or equal to the period. Then instead of rate monotonic, we are going to use deadline monotonic, and therefore task 1 will have the highest priority, task 2 the next highest, task 3 the next highest, and task 4 the final, the lowest priority. Whereas if deadlines were to be equal to period, then task 3 would have received the highest priority. So that's the difference between deadline and rate monotonic. And you can compute kind of what response time one is going to see by, again, solving this equation. So now for this situation, that deadline, where deadlines are not less than equal to period, we cannot apply those formulas we had for the two formulas I talked about, right? N times nth root of 2 minus 1, we can't apply that, and we cannot apply the product formula either. They are only applicable when t equal to d. So when we are in this realm, you basically have to assign the priorities according to deadline monotonic, and then you are going to test using an adaptation of this algorithm where instead of t sub I, you will have d sub I. And then you are going to check whether that priority works. Okay, so slight changes, but one has to work. So now let me ask you a couple of things. Well, or maybe we'll just discuss it. So in this whole framework that you have seen, what is happening is that the priorities we give to the task are purely a function of their timing property, right? I mean, the more frequent the task or closer its deadline, we give it the highest priority. So in other words, what we are saying is that when it comes to scheduling, we are giving more importance, so to say, to the things which, the tasks which have a closer deadline. But if you reflect, the importance of a task in reality may not have anything to do with the timing. So we may very well have situations where I may have important tasks which have very long periods. They come relatively infrequently. But what we want to make sure is that when they do come, they get the highest priority. So like, for example, it may correspond to the most important sensor, and we want to make sure that it doesn't miss its deadline. So, but what will happen in our framework that we have developed thus far is that the task which has is more important may actually end up being given a lower priority and therefore may miss deadlines. Then there are other real world issues. Another issue that we often face is that tasks don't arrive strictly periodically. And I think one of you had raised this issue last Monday, that what happens if task doesn't arrive? And in reality, that would be the case, right? The tasks are coming as a result of some interrupt or some packet arrival. So they may be approximately periodic, but they may have some jitter. And so again, this we have to somehow sort of account for it. Another challenge that we face is that the tasks may be sporadic, as in they're not even periodic with a jitter. They just are asynchronous tasks. How do we handle those? What do you think we can do about a task which is sporadic, like an asynchronous task? There is no period assigned to it. How would you handle that? Any 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 sort of suggestion on how you let's say we have all this theoretical framework that we have developed, and now I suddenly give you a task which is aperiodic. Can you think of a way of sort of incorporating this into our framework?
It might still have a deadline, like even if it's not periodic.
Oh, sure, it will have a deadline. Yeah. So it's
So
not
we can,
periodic, but it has a
yeah.
deadline. Yeah.
So we can probably use that in our formulation, like because we have to complete it before the deadline. So
True, but you still need some notion of a period also, right? I mean, to be able to check. So usually, when it comes to sporadic task, one of the ways you can say is, what is the minimum separation between two arrivals? Okay, so in the sense that yes, I may have this asynchronous stuff coming in, but I do need to know that what is the minimum gap between two arrivals of this task. If I know that, then I can use that as my period. It will be very conservative, but I can still make all the guarantees. If the application is unable to give that to me, then I really can't schedule it, right? I mean, if I say there is an asynchronous event and two successive events can come arbitrarily close to each other, then in theory, I can have a whole bunch of them come within a short period of time, and then the answer is I can't schedule it. So in order to work with sporadic tasks, you will at least need to know some sort of a minimum gap, or you will need to know some upper limit on number of tasks that can arrive in a given time interval, right? Otherwise, you can't really do much about it. So that's sporadic tasks. Another issue which comes up is, thus far we assume that the tasks don't interact with each other, right? That they never use a shared resource. But in reality, that's not the case. They may need to use, let's say, a same radio or the same sensor, or maybe even some data structure, right? So how do we do it? And oftentimes it may be that one task is producing a value that another task needs. So tasks interact I mean, rare are the systems where tasks are truly independent. Then another challenge we face is that tasks oftentimes lock out interrupts, right? What I mean by that is that in order to do things without interference from other tasks or the operating system, one of the surest way of handling that is that you just disable interrupt and re-enable interrupt. So by disabling interrupt, you are making sure that nothing can interrupt the processor, and therefore nothing can cause another task or even the OS to run. And oftentimes tasks do it, right? Because what happens is sometimes you will encounter hardware where there will be super tight timing constraints. Like they may say, write this value and within 1 microsecond write this other value, these kind of things. And those are very hard to do by if the control were to go back to the OS. So usually what happens in these cases is that you will lock out the interrupts just to make sure that you keep control over the processor. The problem is that doing this kind of locking out of interrupts really messes with the whole framework, because remember, one of our assumption was tasks can be preempted, but that would no longer be true. Next up is the is this situation. What if deadlines are greater than period? So what I'm saying out here is, let's imagine there is a task which comes every 10 time units, but the deadline, but I'm okay if it finishes 15 time units after arrival. So now what will happen is a task will come at t equal to 0, the next one will come at t equal to 10. But I'm saying that that first one which came at t equal to 0, I'm okay for it to finish at t equal to 12, for example, or even t equal to 15. The problem in this is that multiple copies of a task may be active simultaneously now, right? So in my example, after t equal to 10, it's possible that the first task, t equal to 0, has not finished, and I have another copy of the same task. And if you think about it, the period of a task and the allowed deadline of a task are truly independent, right? I can have something which is very frequent, but I can have a relaxed deadline for it. For example, let's say I have a task which is playing out a sequence of images as a video on your TV screen, then it doesn't really matter if there is a delay in that process. So it's possible that from the time the video arrives in the processor of the television to the time it is displayed, maybe it can take a second to do it, right? That's the latency. But I do know that frames of this video are coming every, whatever, 30 milliseconds or something like that. So latency and period really are two independent things. And so it's very well possible that you may be in situations where the deadline is more than the period. And then you have to deal with this issue of multiple copies. Then another challenge comes from when you have to power manage the processor, right? We talked about earlier in the previous, one of the earlier lectures, that how we can shut down the processor, how we can change its frequency or change its frequency and voltage both. And usually these things are done by sort of hardware in concert with the operating system. Okay, so that can cause you problems. And then finally, and very commonly nowadays, we have this situation where a processor may have multiple cores, okay? Multiple physical cores, and often in some cases, multiple threads, as they call it. So like Intel processors, for example, often allow 2 threads at the hardware level to run concurrently, sharing the same processor. Okay, so basically what happens is while one thread is waiting for the instruction to be issued, the next thread kind of takes over. Okay, so again, in these cases now, not only we have to decide when to run a task, but we also have to decide which core to run it on. So all these things complicate the simple picture that sort of I described. And the next slide set, which I'm going to transition to now, touches upon some of these things. Okay, not all. And in its full glory, the scheduling problem is intractable. So very soon we run into the world of there are no results of like how to do it optimally and all. You have to rely on various kind of heuristics and whatnot. But if you want, so I guess at some stage you kind of face this issue, which is once things get too complicated, it becomes very hard to give guarantees. And in this world of real-time embedded systems, in many cases, you are in a situation where you want to be able to offer guarantees. And what I described with this whole rate monotonic and deadline monotonic, you do get that guarantee, namely, if you assign the priorities in that manner, and if your set of tasks comply with the restrictions that we have, then you are assured that deadline would be met. And we'll also see that for some of these other these cases that I have identified out here in the slide, again, we can still give assurances. Okay, and that's very crucial because you don't, again, some of these safety critical systems, we want to make sure that they don't miss a deadline and cause problems of safety, for example. Okay, so let's see. So I want to transition to how we can address some of these issues. Okay, so just a sec. Okay. So in this slide set, I'm going to touch upon some of the issues, but not all. So we saw this complication slide. So let's look at some of the things, and you'll see that the ways to handle some of these things are a little bit hackish. But I wanted to give you a sense of like what happens, like, because your operating systems may simply provide you the ability to assign the priorities. The rest of the stuff, how you deal with it, is something that's left to the developers. So one issue which comes up is what happens if there is a transient overload. So, and by that, what I mean is, let's imagine that you did all this fine stuff and all, and then your processor is heating up, and so the hardware at the lowest level decided to slow down the process. So when the hardware decides to slow down the process, then some amount of processing capacity disappears. So that's one very common scenario. Another common scenario is that you may have tasks, and you may know their worst case execution time, but the worst case execution time, if you were to go by those, then you will have an unnecessarily fast processor. So you may say, hey, what I'm going to do is I'm going to go by the average execution time, and then I want to see what that in case my actual load exceeds, then I want some non-critical task to miss its deadline. I'm okay with that, right? So the concept being that critical tasks should meet deadlines, but non-critical tasks can miss their deadline. Okay, so that's again a very common scenario that you enter into. So it's this latter scenario that I'm talking about here. So a bunch of tasks, and what you see out here is the peak execution time, which is here. So that's the worst case execution time. And then there is an average execution time, and which is shown out here. And this can happen just sheer because of data dependence. Oftentimes you have some sensor processing algorithms, which if the sensor value lies in some specific regime, may return very quickly, but in the worst case, they may take a long time. So for example, if you are compressing frames of a video, then depending upon how complex the scene is, some of the compression algorithms take different amount of times, okay? Or likewise for speech, sound signals and all, same kind of thing, that they may take varying amount of time. So in this particular case, for example, for task 3, peak execution time is 80 time units, but the average case time is only 40. And we are given these periods, and we are also given this criticality, which is how safety critical this task is to us. And in our particular case, task 1, 2, and 4 are safety critical, but task 3 is not safety critical. So all things being equal, what my preference as a designer would be that if there is an overload situation, then task 3 should be the one which should miss its deadline. Unfortunately, what would happen in this case is that because we are assigning priorities according to the period, then task 4 has a priority which is lower than task 3 just because of the period. And therefore, what will likely happen is that if the processor slows down, then task 4 is the one which is going to start missing its deadline. So what can we do about it, right? So let's deal with this issue. Okay, so one thing which we could do is we can say that what about, let's ditch the whole theory of rate monotonic and deadline monotonic and all, and what if we were to simply assign priorities according to importance? Right? I mean, what if we were to do it? Now, the problem with that is that then, as we saw when we were motivating rate monotonic, that we can easily miss deadlines in that case, right? Even in the good case because of what is happening. So we need to somehow find a way around it. So the way, the trick that is done is that we start splitting the tasks. So what we will do is we will split the tasks so that my priorities according to timing align with criticality. Okay, so let's look at a very simple example. So now in this case, I have just 2 tasks, right? First task has computation times 3.5 and period 10, and deadline is also 10. And the second task has a computation time 7, period 14, and deadline of 13. So looking at this, you would say, okay, deadline monotonic, I'm going to assign lower priority to task 2. Except it so happens that task 2 is a more critical task. So I want to make sure that if it comes to missing deadlines, task 2 meets the deadline, or we would like to prefer that task 2 meet the deadline and not task 1. Now, flip side is that if we were to make priority of task 2 higher, okay, then unfortunately task 1 will miss its deadline. As you can easily see, if we make task 2 higher, then at t equal to 0, task 2 will finish at time 7, and therefore task 1 will absolutely miss its deadline. Okay, so we are kind of in a no-win situation out here, right? I mean, if I assign task 2 the higher priority, then task 1 misses its deadline. If on the other hand, if I assign task 1 the higher priority, then I have a problem with my critical task potentially. Okay, so what should we do? So this is where kind of a trick which is used is that we split tasks. So let's imagine that we take our second task, which was a task coming every 14 time units and took time 7, and it had a deadline of time 13 after arrival. Let's split it into part 1 and part 2. So we literally think of it like some function, and we somehow magically divide it into 2 halves, part 1 and part 2. And now what I have is I have a task which is coming every 7 time units notionally, and it will take 3.5 time units. And I'll have to make sure, except that even ones will correspond to part 1 and odd one will correspond to part 2. And then my deadline will have to be 6 in this case. It would be 6 because my original deadline was 13, and I have to take the more stringent of the two. So I have this new task set now, which is equivalent to the preceding task in the sense of functionally what it will accomplish. But this one now has a property that my criticality, namely task 2 is more critical, aligns with what my scheduling algorithm will do, which is task 2 has a higher priority. So by doing this kind of splitting, we managed to realign criticality and priority. Do you see a problem with this approach? Like in practice, what hurdles you see in applying this strategy? I mean, chop it up into 2 halves, and we can play this chopping game until my more critical tasks have shorter periods or shorter deadlines.
I think you need to have a tight control over when these tasks are occurring.
Well, that we easily can, right? I mean, part 1 can finish, and at the very end, it can have a time event which part 2 is waiting for, right? So I could do that. So that's not a hurdle. I can have that level of timing control over when they will start. But you're kind of on the right track. So think also. So I mean, how in practice, how would you divide a task into 2 halves? That's where kind of the challenge comes, right? I mean, a lot of our algorithms have complicated loops and if then else and these kind of things. Trying to take a complicated algorithm and then kind of cleanly dividing it into part 1 and part 2 so that part 1 takes half the time as the whatever each part takes equal time, or in general maybe you have to divide it into k ways. That's insanely hard, right? I mean, so that's where this method kind of falls apart, and very soon you are splitting in between the loops and in between the bodies of iteration body. And also realistically, I mean, this thing can work for some simple stuff, but not in general. But as a strategy, one could imagine kind of, if you can do it, then it does give you a way to approach this problem, splitting and then aligning the things. Okay, I'm going to skip a couple of slides. Sporadic, I kind of, yeah, so sporadic task. So these are irregular tasks, right? So these are tasks which are Non-periodic, they can come at some point in time, but they don't come regularly. So how do we handle this? And again, there are always such tasks which are present. And one of the ways I could do it is I can basically say that, look, imagine that there is a sort of a period associated with these things, right? I mean, so I could take the minimum inter-arrival time as a period and kind of work with those. So variety of techniques are used to handle these things more efficiently. One approach is we'll say that there is a very high priority task, the highest priority task, and it's going to come every so often, and it will check whether any sporadic task is waiting. Okay, so the sporadic tasks arrive and they go into a queue, and then meanwhile this highest priority task comes and then it runs it. Okay, if the sporadic task is activated and the queue is empty, then the processor has to just idle. So we are wasting time. So it's not very smart. So there are smarter variants of the strategy where basically if the sporadic task is activated, if this, you can think of this highest priority task as kind of like a server. So if the server is woken up and there is no sporadic task, then maybe we can halt the processor, or maybe we can let some other task run. So these kind of strategies are used to kind of handle this particular case. So there is a fair bit of theory around these things. You can think of it as this task which is coming every so often is kind of like a server, and you can now reason about that if your stochastic task, if your sporadic tasks are arriving according to some sort of time distribution, some stochastic process, you can think of it as in terms of a queuing theory kind of a framework, right? There is a queue and there is a stellar, namely the server task, and what would be the delay characteristics of this queue. So there's this whole queuing theory kind of approaches one can use, and that's what people do. You can even reason about what could be the worst case deadline and things like that. So there's a fair bit of work. I'm not going to go into this, but just wanted to let you know that there are these kind of enhancements that exist. Now, the other issue which I touched upon earlier is uncertainty in execution time. So very often it happens that the worst case execution time and the average case execution time are far apart. In fact, in some of the common benchmarks that exist for embedded systems, that ratio is as high as 50 or even 100. Okay, that is, the same algorithm may take like a couple of order of magnitude more time depending upon the data value. So how should we handle this? So, well, if we have this kind of dynamic range, if we were to design using the worst case execution time, the system is going to be very inefficient. If on the other hand, you design it for the mean execution time, then you may be running into deadline problems all the time. And this problem has occurred. So this issue people used to face because of those transient because of the algorithms being of this nature. But in recent times, we have also begun to face problem that our processors have gotten very fast, and for reasons of controlling temperature, heat dissipation and all, at the hardware level, they often do frequency throttling to keep the temperature under control. And so what may happen is that the execution time may change because of that also. Another challenge that we are beginning to face is that as the silicon technology has shrank, so when you get parts coming off the fabrication line, like same processor, same multiple copies of the same processor, they often differ considerably in their speed. So what may also happen is that your algorithm may take different amount of time when it is running on different copies of the same hardware. So long story short, we are facing this challenge that what we thought was a relatively predictable notion of execution time is actually kind of far more complex. I'm sure you may have heard about like gamers who overclock their the processors on their computers. All those kind of things happen. So in recent times, there is this whole area of computing which has emerged, which goes under the name of approximate computing. And kind of the idea is that I would design my system, but if the processor is slower, then I am going to run an approximate version of my algorithm. Or more generally, you can say, what if I were to design algorithms which scale their quality based upon how much was the speed of the processor? So the process, I'm given a certain amount of time, and if I'm running on a faster processor, then I will just produce a better image, or I will produce a more accurate result. Maybe I'll use a larger a more accurate neural network and things like that. So you can imagine all sort of algorithms where we can do this kind of scaling. So it's an area called approximate computing. So there are a variety of approaches of dealing with this kind of issue. So I'm going to describe one of the early approaches that people did, and then I'm going to describe kind of the approximate computing approach. So one approach that early on people viewed was, what if I create multiple versions of a task? Okay, and kind of the idea is that I have a precise version which will take more time, but it will give me a high quality result. And I will have a second version, an alternate version, which will take less processing time, but will give me a lower quality result, just an acceptable result. And we can kind of use that. So for example, let's say I have a task for which I have a primary algorithm and an alternative algorithm, as shown in the slide. And the primary algorithm, worst case, takes 20 time units. And the alternative algorithm, worst case, takes 5 units of execution time. On an average, though, the primary algorithm takes 7 time units and the alternative takes 4. So as you can see, in worst case, primary is pretty bad. But in average runtime, it is only factor of 2 off. And it's the same task, so the period is the same. So a reasonable strategy would be, I'm going to attempt running the first algorithm, and if it turns out that it's taking too long, then I'm going to switch to the alternative one. So what would your strategy be? So you have a period of 15. So when your task arrives, you have a choice of this primary or alternative. And you are going to, so what do you think is a reasonable strategy to execute, to perform this task, so that I maximize the result quality? So clearly running the alternative always will work, right? I mean, I will worst case 5, I will finish comfortably before the deadline. Clearly running the primary can result in failure, because in the worst case, it can take time 20 and my deadline is only 15. In the classical model, I would have gone only by the worst case execution time. But do you think you can do better?
You can probably start parallel execution on both primary and alternate, or maybe you can start with primary, and if it takes more than 7, then you can switch to alternate. You'll still complete within 11 time units.
Okay, both are reasonable strategies. I can do both, but the only thing is I don't know what does it mean to do both. But let's say I'll run a little bit of primary, a little bit of alternative, a little bit of primary, a little bit of alternative, right? I can kind of multiplex like that on that processor. I could do that, or like you're saying, I can run until time 7 and then switch. Do you think is that a good strategy? Should I run until time 7 and then switch? Because then I'm finishing at 11. I'm still leaving some CPU unused. Could you improve the quality of your results? So actually this figure shows the answer. Okay. So think about the following. I start with primary, right? Because my goal is to maximize the quality. But there will be a point of no return in the sense that at some stage I have to abandon primary and still leave enough time to finish the alternative. But the alternative takes 5 time units in the worst case. That means I must abandon primary no later than t equal to 10, because if I do it any later, then there is a chance that I will not even finish the alternative. So as shown in the figure, my strategy would be I will start with primary, and if the primary finishes before t equal to 10, great. If the primary does not finish by t equal to 10, then I'm going to switch to abandon and I'll switch to alternative. And then I know in the worst case, I'm still going to finish the task. Okay, so that would be my optimum strategy, right? Everyone gets it, right? So that's what we are seeing on the slide, which is this is the point of kind of no equal to 10 is the point of no return, right? So uh, so that gives us one strategy. Now, of course, this primary versus alternative is kind of a very binary way of looking things. More generally, what if I have algorithms which, as I was saying, are designed to give me this this kind of approximate thing? I can run them. They can give me a whole bunch of different qualities. Okay, so for example, let's say if you were trying to compute some numerical result, then maybe I could structure the algorithm so that if I give it more time, it is going to give me more digits of accuracy, right? So let's say the result was some sort of a real number, and the precision of the computation can depend upon how many clock cycles or how much time I'm willing to give this algorithm to run. So many iterative algorithms can have this characteristic, that is, you start an iteration and then all they're doing in every iteration is they're just improving the accuracy. So in this particular case, I've given examples of like iterative division algorithm, or oftentimes you can do arithmetic in a bit serial manner so that you start producing results from the most significant bit, and then in every iteration you produce the sort of more and more resolution. So that's one. Can you think of some other examples from kind of algorithms you see which have this characteristic where I give it more time, they give me better quality results? Just from your daily sort of experience with computer systems, do you see what kind of tasks are amenable to this thing where algorithms given more time give me better results?
Like heuristic based algorithms, like we have, I think, placement in VLSI design, let's say, or more epochs in machine learning.
Sure. Okay. So more epochs in machine learning, that's a great one, right? I mean, if I'm learning a model, right, or tuning a model, then more epochs, generally speaking, will give me a better result. Okay. VLSI placement, great example too. Google queries, right? I mean, I'm pretty sure the diligence with which that search happens probably depends upon how loaded the Google infrastructure is at the time. Any type of search algorithm is amenable to that, right? Because search algorithms search some space and they can return quicker by searching less, or they can go deeper into search, right? So that's an example. Maybe you have a filtering algorithm which is filtering a signal, and how many coefficients it uses to filter can be a function of how much time we give. or I may have a control algorithm which is operating in this manner. So if you kind of reflect, we are actually so many things when we process sensor data, when we process search queries, when we train machine learning algorithms. Even let's take a neural network, right? I mean, I can easily, there is this class of neural networks where I can change the bit precision, right? So you give me less time, I'm going to compute that neural network at a lower precision, right? So there are a variety of these knobs. How many coefficients, how many bits, do you use integer versus floating point versus double? All of these things kind of fall into this category. So there's a rich space of algorithms out there, or you can always design the algorithms this way. A graph search, same story, right? I'm trying to find the shortest path. Well, maybe I'll find a lot of these algorithms are optimized, designed in a greedy manner, right? They start searching, and then as they encounter better ones, they replace the preceding one. So again, more time we give, the more they will search, and presumably a better result that they will get. So very common place to have this kind of possibility occur, right? More time, a better result. So these kind of things, the technical name for them is IRIS task, increased reward for increased service. Namely, if I give it more resources or more time on the CPU or more memory or more bandwidth on the network link, they're going to give me a correspondingly better result. So there are a variety of ways of dealing with this, but one very common model for this kind of stuff is that we think of our tasks to have a mandatory part, which is basically saying if you don't do the mandatory part, then effectively I get no utility from performing this task. I failed. Okay. And so we want to make sure that the mandatory part is met. So, like, for example, in my Google search query, maybe the mandatory part would be that within 1 second, we must return the first page of queries. Okay. So that may be the hard deadline. And then the softer deadline may be when do the queries get filled in those, like when you do the Google query, you see, right, multiple tabs at the bottom. Maybe the other tabs may be filled more slowly, and how many tabs are filled, right? I mean, those kind of things could be are less time critical. So there's a mandatory part where I absolutely have to respond with an initial result in a timely manner with at least a minimally acceptable quality. And then there is an optional part, and kind of the idea is that this optional part, I would like to, there are many different ways of framing the problem, but one common way is that there's an optional part, and the more you do the optional part, presumably the result quality increases, but perhaps to some limit, right? I mean, at some level, let's say you are computing output on a speaker, okay? Well, after a certain number of bits, you cannot even notice the difference, right? Or likewise, if you are measuring some sensor value, maybe processing bits which are almost in the noise floor is pointless. So the optional part may have very complicated relationship with the result quality, but presumably, sort of to some degree, doing more of the optional part is going to help to some extent. So viewed in this framework, the classical model, the one which we discussed earlier, basically says optional part is zero. Everything is mandatory, right? And basically the view there was that if you fail to meet the mandatory, then you fail. So in this framework, we are saying do the mandatory for sure. If you are unable to even do the mandatory, then we will consider the system having failed. But if you do the optional, then try to maximize some notion of overall system utility, right? I mean, so I want to meet them. So the whole problem now becomes I want to meet the minimum, that's a constraint, while maximizing the overall utility. So I'll have a set of tasks. Each task will have this MI and OI, okay? And we are basically going to say for every task, the mandatory must be met. And then I will have some sort of a utility function, which will basically, given the optional parts which are computed, will say how good the system is. Okay, that's kind of the viewpoint out here. So one way of framing the scheduling problem now is like the following: that for every task, I have a reward function, okay, or a utility function. There are many different names. We're calling it reward out here. So R of X, and X indicates how much time we gave to the task. If the time we gave to the task was less than the mandatory, so M, if it is less than that, then the reward is 0. If on the other hand, the time that we gave to the task is more than O plus M, so O is some sort of the maximum optional value that I want. So if it is more than O plus M, then it's unnecessary, right? That is for values of X greater than O plus M, the reward I get is same as the reward at O plus M. Okay, so that's capturing the point that beyond some point, there is no additional utility. And in between, where the amount of time I give to the task is between the mandatory and this O plus M threshold, I will have some function, and it's reasonable to expect that this function is probably going to be monotonically increasing with X. That is, we give more X, then R of X will be higher. So essentially, our scheduling problem now becomes this, right? I mean, that we are given such a reward function for each task, and my goal would be to maximize the overall reward of the system. Okay, and that's kind of a general framing. You can think of this for all sort of things. Sharing a processor is how we were thinking, but you can imagine this is how you might want to also decide sharing limited resource of any type, like network bandwidth or storage or sharing of sensors or whatnot. Okay, so all of them can be viewed in this particular framework. Now, intuitively, how do you think you will address this? Like, no, so firstly, in general, this problem is intractable, as in, again, sort of for which there are no efficient polynomial solutions. But let's say you are faced with this problem. Can you suggest some heuristic strategy to approach this? So what would your step number one be? Step number one would be you have to make sure that you can meet the mandatory, right? I mean, because otherwise the whole system is useless, right? So we have to make sure that for X equal to M for every task, things are schedulable. But let's say we have done that. Now, let's say we have one additional unit of resource, right? One additional unit of processor time. Which task would be a good, intuitively, which task would be a good candidate to give that resource to? Any thoughts? Like what would be a good strategy to spend? Which task would you spend that resource on? What would be the guiding principle?
The task which provides the greatest reward for that particular X.
It's the greatest increase in the reward, right? I mean, so in terms of economics, it is the task which has the largest or the highest marginal gain in the reward. So DRX over DX is the highest, right? Intuitive. It's kind of like a gradient kind of a concept, right? I mean, you want to go to that task which, given that additional increase in X, results in the most increase in the reward. So that could be a greedy strategy. Not necessarily the best one, but this is an optimization problem. It's a non-linear optimization problem, very similar to what we encounter in a whole bunch of other places. And we have seen, at least in neural networks and all, that gradient descent often work pretty well. So you could approach it this way. Now, the challenge that we face is that usually these little r functions are not some nice mathematically behaved functions. They're often could be far more complicated, or even just be given by human users. Okay, so you have a highly nonlinear optimization task. There is no optimum solution, but a reasonable heuristic that often works is just doing gradient descent or gradient ascent, I guess, in this particular case, because you're dealing with the world. And so you greedily allocate resources to the task which has the highest marginal utility. And that could be one approach. Anyways, that's the framing of the task. Okay, so this whole, like I said, this whole area of imprecise computation and approximate computation and all, after some initial early work in the space in 1990s, again got a revival in recent times. Okay, and it has gotten a revival in recent times because of the changing characteristics of the hardware and the networking platforms. So two things which have happened. One, as I mentioned earlier, that we are running on more shrunk down silicon technologies, and it turns out that they inherently have these characteristics that the processor speed can vary from one instance to another, or processor speed can vary from depending upon the operating condition with temperature and things like that. So it has become very common that we are in this world where it's very hard to make hard guarantees. The other thing which is happening is that we are running on more general purpose systems. So it used to be that for the longest while, embedded systems were basically done with these very carefully designed hard real-time systems and all. But increasingly, we also see that we are just running these things on more like Linux and or even on cloud services and all. And so a mindset which has also emerged lately is that instead of doing hard real-time systems, for a lot of applications, we can run them on these more general purpose systems, but we design our algorithms to be of this nature, where they can, given more resources, they will do better. So there is a term which is used quite a bit, and that is called quality of service. It comes from networking community, but is also available. It's also used in multimedia and all. And kind of the idea is that instead of saying that there is a hard service requirement, my goal is to maximize quality of service, maximize the overall quality of service. And usually it is some combination of the two, that I may have some task or some clients to which I have to give hard guarantees, and the others are more flexible. In networking world, there is, or even cloud computing world, there is another term which is used as service level agreement, SLAs. Okay, so these are all sort of attempts to capture this notion that I may have a mix of clients, clients with like very hard needs, okay, and those I want to make sure that I don't fail to meet those contracts, because if I do, then the cost is very high, sort of high penalty. But then there are all these other elastic loads, okay, which I would try to keep happy so that they don't dump my company. But on the other hand, I don't have this sort of hard requirement with respect to them. So more typically nowadays, this is what you would find. And honestly, if you kind of think, step back and all, a lot of things that classically would have been put under hard real time are frankly not hard real time, right? I mean, in the sense that some failure or an occasional hiccup is tolerable. So while it is certainly true that you don't want your car to crash and all, but on the other hand, if there is a skipped video frame and all, that clearly doesn't matter. Okay, so this mindset has become very common, and of course it makes the scheduling task harder, but it also makes it easier to design more efficient systems. Okay, next issue is dealing with shared resources. So again, the assumption we had previously was that tasks are independent, but in reality, tasks interact with each other. And if you recall, when I had described multitasking earlier on, I had described how there are semaphores in various ways by which tasks can interact with resources, they can interact with each other. The problem is that the moment tasks interact with each other, we have a possibility that timing constraints may not be met. So imagine, for example, a high priority task which uses the same sensor as a low priority task does. And let's say the high priority task comes, and it's possible that the low priority task has taken the resource, already has the resources, already using that resource. Well, at this point, I can't simply bump the low priority task off, because if we remove the low priority task, then the high priority task will not get the resource because the low priority task has the resource. So the high priority task can now be interfered with by a low priority task. Previously, when we did the analysis for response time, we only had to worry about the higher priority task, right? Because the only worry we had was that I have the CPU, but some higher priority task becomes ready and takes the CPU, right? So that is why we had that term of interference by high priority task. But the moment you have shared resources and all, then you have the possibility that a lower priority task can affect your timing. And not simply shared resources, right? Maybe I need the input from the low priority task, right? I mean, low priority task is producing some data that I need. So all these possibilities are there. So this phenomenon is called priority inversion, okay? Kind of the idea being that there is a low priority task which has something which the high priority task needs, and therefore is preventing the high priority task from running, and that phenomenon is called priority inversion. So let's take an example of the kind of complex situations that may arise. So let's imagine there are 3 tasks, task 1, task 2, task 3. And what we have is the situation that, so let's say task 1, task 2, task 3. Task 1 is the highest priority. Okay, so this is high, highest, lowest. Okay, and the situation we have is the following, that this task 1 and task 3 use the same shared resource, some shared semaphore S. Okay, and what happens is that this task 3 has grabbed that resource. So this resource is with task 3. And now what happens is task 1 becomes ready, and we are blindly following our scheduling strategy. So task 1 will bump task 3 off, and CPU will go to task 1. And task 1 starts running, and but as soon as it runs, at some point it will need this resource S. So task 1 will stop, right? It needs the resource. Yes. But meanwhile, let's say task 2 has come, and it will grab the CPU. So task 3 cannot run, but task 3 has the resource, and task 1 is waiting for task 3 to release the resource, and meanwhile task 2 is ready to run and will grab the CPU. And if task 2 runs for a longer time, then task one will keep waiting. So what is happening now is that task one is being, so it's reasonable to assume that if task one needs the resource that task three has, then it has to wait for it. There's no choice. But task one is now also being interfered by task two, right? Because even though task two did not grab the resource, right? And task two is lower priority than task one. So we and this phenomenon can be very complicated, right? Because what happens is task two comes, it finishes, task three runs for a little bit, still is in the semaphore, the shared using the shared resource. Again, another copy of task two comes, and that situation can last for a long time. So it's possible that task two may cause long durations of interference, and then task one may miss its deadline. So intuitively, how would you address this problem? What can we do to prevent the situation that task two prevents task one from running? Our goal is, if task one needs the resource S, then I want it to get the resource as quickly as possible so that it's a high priority task, so it should be able to run. So what would you do? Is there some way we can prevent task two from running? So why is task two running compared to task three? What causes the CPU to be given to task two?
The fact that task two has more priority.
Excellent. Okay, so it has more higher priority.
So task one should also be able to take it from task two.
Say it again. Task one should also be able to what?
To take it from task two, to take the resources.
No, task two does not have the resource, right? The resource is with task three. And task three is using the resource, but task two is higher priority than task three, and therefore task two is running, right? So is there something you can do to address that situation? Well, I mean, intuitively, I want to give task three the higher priority, because task three is preventing task one from running, and task one is even higher priority than task two, right? So intuitively, what we need to do is something along the lines, we say, hey, task three, you have the resource S, it's needed by task one, but task two is preventing you from running, so maybe we should give task three the priority of task one, right? Because task three is blocking task one. So what I'll do is I will make task three's priority artificially higher. For the duration, it had the resource that task one needs. So it's kind of like the servant of an important person becomes like the important person for that duration, right? Because it is in service of that other one. So normally, in the absence of shared resources, task one will have high priority and task three will have the lowest priority, and everything will be okay. But if there is a shared resource which the low priority task has grabbed, and a high priority task needs it, then I'm going to make the lowest priority task inherit the same priority as the high priority task, and thereby avoid this problem, right? So that could be our strategy, right? So because in the absence of that, we kind of run into this problem that these intermediate tasks can basically block task three for a long time, and then for task one, even though it's the highest priority task, it has to wait forever. So That's the game we are going to play intuitively, which is we are going to mess around with the priorities. So the priorities are going to be no longer fixed. They will have some degree of dynamic flavor to them. Okay, in order to deal with this problem of priority inversion. So, so basically this slide is summarizing what I said. What would we prefer? We would prefer that task 1, because it's the highest priority task, should not have to wait any more than strictly necessary, right? So, but because of this task 2, that's no longer true. So what we are going to do is we are going to mess with the priority of task 3 so that it quickly releases the resource, and then task 1 can go its own way. Now, all of this sounds kind of esoteric and all, and like, yeah, right. But actually, one of the biggest event in this space really happened because of a huge fiasco that happened in late 1990s. So these were the early days when this whole area of rate monotonic and all real-time systems and all were coming into place. And there was a mission to Mars, and there was a robotic vehicle called Mars Pathfinder, which had been sent there. So I imagine most of you were probably not even born then, or just about born, perhaps. So in this case, what had happened was that this robotic vehicle was enclosed around inside kind of airbags, basically, and then it had bounced around on the surface of the Mars before coming out. Okay, so it was a pretty cute landing to deploy this rover. And then it had sensors and all, and it basically collected data and sent back to Earth. It's made locally here at JPL. Except what happened was, after a few days into the mission, it basically started facing resets. Essentially, the system was crashing, and obviously data were being lost. Okay, so it would crash, reset, restart. The same process went on and on. And media reports were along the lines of like there were software glitches, and because there was overload on the computing system, and then after some time, NASA JPL managed to fix it. Okay. What happened under the hood was exactly the scenario that I painted. They were running a hard real-time system, and they had this priority inversion failure. So basically, sort of somewhat of a hand-wavy manner, what was happening was that they had a bunch of tasks. They were using an operating system called VxWorks, which still exists. It's the most well-known of the commercial strength real-time systems that there is, made by a company called Wind River, out of Bay Area. So basically, they had a bunch of tasks, and they had a situation there that there was a high priority task. Its name was BCDIS, doesn't matter what the name is, and it was being blocked by a much lower priority task, whose name was this ASI MET, which was some sort of a sensing and meteorological task, and which had grabbed a shared resource. And after this low priority task had grabbed the shared resource, it was being preempted by a medium priority task. Okay, so exactly the scenario I had painted. This is task 1 in our hierarchy. This was task 3, and this medium priority task was task 2. So that's what was happening. And as a consequence of this high priority task, this guy was missing its deadline. Moreover, in that system, there was, because they anticipated, like, I mean, once you are sending something to Mars, You can't just go and manually hit the reset button. And also, of course, they designed for this thing. So they had an even higher priority task, okay, called BC Sched. And this BC Sched, what it was doing was it was like a planning task. It would figure out what would happen in the next few transactions on the bus in this embedded computer. And it would check whether things had finished from the previous cycle, and it would see that BC disk was not finished. And if that was the case, then it would reset the system. So essentially, the way they had designed the system, and which if you are ever in a position to design a safety critical system, you absolutely must. That is, there should be some fail-safe mechanism, right? That if other things haven't finished and all, then you need to bring the system back into a known sane state. So this BC scheduler was checking whether BC disk had finished, and if BC disk hasn't finished, which was indeed what was happening, then it would reset the system. And what was happening was that this task, the ASI MET task, it was some sort of a, like I said, some sort of a scientific data gathering task. And they had designed it for some envisioned workload, as in like how much interesting sensor information would be there. And it just turned out that as this robot was moving around, it would encounter more interesting data samples to collect. I'm kind of paraphrasing a little bit. So this task would take more time than they thought it might. Okay, so this is back to our average case, worst case situation. Okay, so they had designed it for some thing, but those assumptions turned out to be not true. So it was taking more time, and the cascading effect of that is what it led to this. So BC Sched basically kicks in and does it. In many systems at the hardware level now, we also have a concept of watchdog timers. And kind of the idea in watchdog timer is, and which is probably what BC Sched must have been using, that in the processor hardware, there is a timer which when you start running, it basically, the moment you start, it will fire at some point, and when it fires, the processor is hard reset. And to prevent it from hard resetting, you have to restart the timer. A little bit like, you know, how the timer apps in your phone and watches work, right? I mean, you start the timer running, and when it hits 0, then the alarm blares. But if you stop and clear it prior to that, then you can restart it. So watchdog timers work exactly like that. So presumably what was happening was this BC Sched must have been using some sort of a watchdog timer. And these watchdog timers are done at the hardware level, so that even if your software goes awry, your system will be still brought back to a sane state. So particularly for remote systems, but in general for any sort of safety critical system, right? I mean, in your cars and all, you also want to make sure the same thing, that something bad happens, the system reverts back to a good known state. In fact, you also have to prepare for the possibility that firmware may be corrupted, and also oftentimes these watchdog timers are coupled together with some mechanism that a new copy of the firmware is loaded. Okay, so that just in case data structures were corrupted or code was corrupted, you kind of fix all of that. Okay, so so that is what was happening. How they fixed it. So again, sort of for these kind of systems, you have to prepare for the worst case. So what they had was they had a replica on the Earth, okay, and together with a tracing logging facility, and they found once this problem kicked in, what was happening. Now, fortunately, this operating system, VxWorks, had a facility where by typing a command on the shell, you can change the behavior of all the semaphores so that this capability called priority inheritance, which is what I was saying, that task 3 gets a priority of task 1, you can enable it. So in with a without like having to re-upload a new firmware and all. By changing a flag in the running system, you can basically change the behavior of all the semaphores. And since everything else that is shared builds upon the semaphore, so this was a clean solution. So basically, what they did was they had to only set a tiny patch, which basically changed how the semaphores in the system were behaving, and then they were able to fix this problem. So that's what happened, and there was a description about this and all, one of the main conferences in this area and all as to what had transpired. Now, why was it not detected and why was it not fixed before, right? So essentially, like I said, these were very early days of real-time systems. So the knowledge about the tools and the knowledge and all were not as commonplace as one might imagine. So what was happening was that this problem manifested itself only when that the ASI MET task was heavily loaded. And what they had done was in testing, and this is where kind of want to comment upon it. Like classically, when we develop software, we test it, right? And how do you test it? How do you test software? Anyone? Like when we say like if you write software, or even better, if any of you have ever worked in industry, how do you test software? Like, do you approach it in any systematic manner? Like, how do you decide what to test it on? Okay, how do you test your own software that you write in your coursework and all?
You can do like I think it's called like unit testing. So
yeah,
like,
okay.
if your software is very complex and it has many different modules, then you can test each module individually and make sure that it has the expected behavior given certain inputs.
Okay, excellent. So unit testing is the notion that I decompose the complex system into its parts and then test each part, right? Unfortunately, but so there are two questions out here. How do you test each part? So all we have done is we have translated the problem into testing of parts, and I guess the other issue is how do we make sure that the composition is still as expected? Okay, so let's do the formal one. How do you test parts? How do you decide that the part is working correctly?
I guess like think of worst case scenarios, I guess, like worst case inputs. For example, if you're testing sensors, like what if they're operating, or what if they're giving you like readings at like their limits, like the operation limits and stuff like that?
So, okay, excellent. So corner cases, or what you're calling as worst case, right? I mean, so for example, if you have designed I don't know, let's say an adder, you might want to make sure that it's working with the lowest values and the highest values, and then you might check for some random values in the middle just to get confidence, right? So usually we test by identifying corner cases, because that is where our loops and branches are likely to suffer from something, and then you test some middle cases. But still, short of an exhaustive testing, none of these things will ever give you any guarantees, right? I mean, because it's still conceivably possible that the failure happens because of the one thing that you didn't test for. And then the other issue is, how do I test that the whole composition is working? Okay, so there good design practices and all partly help out. But in any case, what you described is right on. That's how we test software. And it turns out that these things are not sufficient. In fact, the fact that these things are not sufficient, you also see routinely whenever they say, oh, the hackers found a vulnerability in the software, right? Because what had happened is that some cases which no one thought would be used are the ones which were left unprotected. Okay, some place where you allocated a data structure and it didn't, you didn't exercise that, okay, that path through the code. So your test vectors never tested for those, and that is where the bug was. In fact, one of the favorite tools of people who are doing security analysis is something called fuzzing. Anyone heard of this term, fuzzing? So what fuzzing tools do is they basically throw random inputs at your code or at your hardware, as the case may be, and until they find some vulnerability. Okay, and precisely the idea is that this kind of unit testing and all limits itself to a few test vectors, and they often miss cases where bad things happen, and these fuzzing tools try to probe until they find a vulnerability. So that's what the practice is. But when you are dealing with safety critical stuff and all, it's probably a better idea if we can strongly prove that the system or the software will work correctly, right? So there is testing, which is what we do, versus verification, where we mathematically or through systematically we try to prove that it will happen. So in a way, kind of that whole rate monotonic theory that I described is an attempt in that direction. Instead of just saying, okay, I'm going to pick a fast enough processor and test and see, oh, no deadlines are missed, I'm actually going to prove that for these things are going to work fine. Likewise, we would like to be able to prove that even under shared things, I will not have a missed deadline and all. So for safety critical stuff, kind of the idea is you really want to have a sort of a mathematically guaranteed way of proving properties about your system. Now, of course, it is hard and it's not always doable, but if you can, that would be better. So now we know how to analyze these kind of hard real-time systems, and there are tools and all, but in that era, it was more of a testing approach. So these guys tested, long story short, they tested, they saw the problem, but they couldn't get it to be repeated because it was a pretty low probability event. And so it was kind of dismissed to hardware glitches. And then those watchdog timers that I talked about, right? They are precisely designed for those rare hardware glitches. So this is another kind of thing, right? I mean, the software and people don't talk to hardware people or don't have an understanding, and it's kind of like kind of a bit of a like blame the other side kind of thing, which also happens, right? The system crashes, must be a hardware problem. Other people say no, must be bad software, and no one really ever talks. Long story short, again, so out here, since this was data collection software, it was not a particularly high priority thing. More focus was on getting the entry and landing software right, kind of the actual controls of the space vehicle. So this was dismissed to as some rare hardware glitch, will not cause problem, when in reality, it was actually something, if they had analyzed, they would have been able to prevent it. Okay, so so in those, this whole thing sort of approaching these problems from first principles is extremely useful, because only then you can detect these kind of bugs and systematically eliminate them. So things have changed considerably to now we are in a state where doing formally verifying properties of hardware and software and all for critical stuff is an accepted practice. and I guess things have just become complicated enough that you will not just rely on ad hoc testing, at least not for the safety critical stuff. And also, if you're designing whatever an autonomous driving system for a car or a drone or something, you are not going to just rely on the way we test rest of the software with some QA engineer coming up with some use cases and testing against those. You really got to prove that the system will not fail under a set of assumptions. And of course, it's possible that even those assumptions may not be true. And there are then esoteric issues that may still happen. If you are like a couple of other anecdotes of this nature, in 1990s, a family of Intel processors had a floating point bug where certain floating point numbers would exhibit an error. And likewise, the Java virtual machine had a bug in handling, I think, some division or something like that. So these kind of things are not entirely unheard of, where very high profile, widely used systems have bugs which are very, very problematic. And sometimes they're not just bugs, they are designs which were erroneous. And just over the past couple of years, there are a series of these micro-architectural issues that have been discovered in all our processors, okay? So, and have been a significant source of concern at this point because they have been exploited by malware. So anyway, this is what had happened. We have exceeded our time, so I'm going to stop out here, and next time we are going to just go over how this problem gets addressed currently, but how does this priority inheritance work, and then we're going to take it from there. Okay, so I'm going to stop at this point. Let's see, let me make sure that there are no questions in the chat. Okay. I guess these are comments along the way. So, okay, any questions before? Otherwise, I'm going to stop recording, and then we will do the office, any project discussion. So, but before I do that, any questions relating to the lecture itself?